A dominant theory in the AI industry suggests that models can become smarter simply by talking to themselves. The idea is that if a model corrects its own mistakes long enough, it will eventually shatter its limits and evolve into a superior intelligence. We see this in practice when a model uses chain-of-thought prompting, reflects on its own reasoning, or cycles through a sequence of tool calls. This is inference time revision, improving the answer without changing the model. The alternative is internalization. This is where engineers take external data and bake it directly into the model's weights through fine-tuning, distillation, or reinforcement learning. Current AI discourse frequently treats these as a single accumulating process. It assumes that enough runtime self-correction will eventually transform into the same kind of growth we see during training. This iterative blur makes it difficult to predict the actual trajectory of AI progress. If we can't distinguish between a model being clever and a model becoming more capable, we can't see the limits of the system. The reality is that finite self-correction at runtime and the internalization of new capabilities belong to separate mathematical regimes. To prove where one ends and the other begins, we need a way to test these systems against the strict boundaries of Oracle computability. By stripping away the empirical hype, we can use the math of Turing machines to measure whether a system is actually growing or just spinning its wheels. This framework dates back to Alan Turing's work on ordinals and oracles. It provides a language for what a machine can solve when it is pinned to a specific set of rules. We start by defining a settled deployed system. This is the model as it exists on a server. It includes the weights, the architecture, and any fixed rules for how it updates its state at runtime. In this framework, we treat that entire system as a base oracle, which we'll call Oracle A. Every task the system can perform, no matter how many loops it runs, exists within a specific boundary. We call this the computational layer, or C of A. It represents every task computable by our base Oracle A. Prompting, re-ranking, and memory updates just navigate this space. They move the system within the circle, but never expand the circle itself. Because these reasoning loops rely on rules already present in the system, they cannot generate knowledge that sits outside the mathematical borders of their own base oracle. This raises a central question. Can an AI system bridge the gap to a higher tier of intelligence simply by thinking longer? We can model this by looking at internal self-modification as a rule that produces new versions of the model's own internal machines. High-end models often use nested learning or complex tool use loops to solve problems that a single pass could never handle. But any rule computable by Oracle A can only produce more machines also computable by Oracle A. The system is mathematically closed. This is local closure. Internal procedures don't break the original degree. They just produce more complex versions of what the model already is. Spending more inference compute to let a model think through a problem can improve the accuracy of the result, but it doesn't grant the model a new level of cognitive depth. There is no way to reach an intermediate strength above the base oracle through these finite steps. If you start with the tools in Oracle A, you stay in Oracle A. An internal reasoning loop can explore the absolute limits of its current layer, but it will never organically generate a leap into the next one. The dynamics change if we consider the absolute limit. What happens when an iterative correction process converges perfectly on a final, settled output? This is a stable revision process. It's an approximation where, given enough time, the model's answer eventually stops changing and stabilizes. This stabilized output marks a new boundary called the Turing jump, or A'. Math tells us that any task solvable by this infinite convergent revision is exactly what defines the jump. It's the ceiling of what's reached through trial and error. Because this outcome requires observing a process all the way to its infinite limit, it represents a different regime than the ordinary, finite computation happening inside the layer. We've moved from the within-layer world to the jump-level world. We are looking at the potential of the system rather than its immediate realization. Even deeper layers exist. If we nest these stable limits within each other, we approach higher and higher jumps, like A''. But the core lesson remains. Reaching the optimal version of a current layer is not the same as building a new, stronger one. To move past the jump boundary, the system needs information it literally cannot produce on its own. It requires externally essential guidance. It might be a reward signal, an external engine search trace, or a totally unseen dataset. These are resources that simply don't exist in our base Oracle A. Ascent only occurs through true capability internalization. This is when a new successor system is built, so that this previously external help is now a native part of the model's reasoning. This is exactly what happens during large-scale post-training or architectural retraining. We take the help and turn it into hardware. When a model can natively perform a task that previously required outside help, its base Oracle has shifted. It has moved to a strictly stronger relative level, which we can call Oracle B. The shift, where Oracle A is strictly weaker than Oracle B, is the only rigorous way to define a genuine gain in capability. Recursive self-improvement requires the structural ingestion of external reality. Without new information from outside the loop, the system's baseline remains static. These distinctions allow us to categorize AI progress with precision. Learning, self-correction, and ascent are not interchangeable terms. We use a matrix to classify AI improvements. Row 1, within layer activity. Prompting lived here, inside the original C of A. Row 2, jump level regime. Models iterate to reach the Turing jump boundary. Row 3, cross-layer ascent. Retraining creates a strictly stronger model. This provides a simple test. When you see a claim of a breakthrough, look to see if the underlying rules were updated. If the rules are the same, the model is still in the same layer. By applying this lens, we can separate real architectural progress from the mere optimization of what we already have. It is easy to dismiss these mathematical limits as theoretical abstractions that only apply to the infinite. But in the age of AI, these boundaries define the hard perimeter of what a specific system is capable of thinking. The math of the Turing jump shows us that there are truths an AI can move toward, but it can never possess them without a fundamental change to its own structure. Intelligence does not grow in a vacuum of endless self-reflection. To reach a new level, a system needs to encounter the world outside itself. To build intelligence that moves beyond its initial architecture, we must stop asking it to think harder and instead force it to become something structurally new.